So today's speaker is Huanhuan Li, who will speak about bifurcation splittings of graphs and Leavitt algebras. Please go ahead.
Thanks, Wheeler. First, I would like to thank Wheeler and Gisela for their kind invitation for me to give a talk here. I'm so happy that I have this chance to give a talk at this great seminar. Today, the title for my talk is Bifurcation-splittings of graphs and Leavitt algebras. Actually, this is a recent little result. This is a joint work with Wen, who is my master student, and Le, who is a teacher at the University of Science and Technology of China. And basically, it's like this. We construct a new graph, and then we establish some relation between the corresponding Leavitt algebras. So today, for my talk, basically I have three parts. The first part, I will introduce the new construction, the construction for the new graph. And for the second part, I will talk about a homomorphism we construct between the Leavitt algebra for a given graph E and the Leavitt algebra for the new graph. And then in the last part, this is for final graph case. So we have a classification for these two Leavitt algebras. Okay, let's first. So for E, in our situation, this is a given graph. So it's not necessarily finite. So it's an arbitrary graph. And a graph, we mean we have this data here. So we have two sets, E0 and E1. So E0 is vertices set, and E1 is edges set, and SR are source and range maps. So before we give the definition for the new graph, so we have some notation here. So here first give us two vertices, U and W. In E0, we see U is greater or equal to W if there exists the path such that it is starting at U and it's ending, ends at W. And now give us a subset X over E0, we can define a predecessor of X to be this set. So this is vertex is U such that U is we call PX the predecessor. So this is like this. Sorry.
No, that
any problem?
Muted for a second. So okay. I wonder.
Okay. Yeah. No, okay. Yep. Okay. Then I continue. So this is we call the predecessor of X in the graph E. Okay. Then in the following, we will fix a vertex V in E0. This vertex, we assume that it is it satisfies this. So we have found many edges starting from it, and we have also at least two edges starting at it. So in fact, we call this a bifurcation vertex of E0. So V is fixed, so it's always a bifurcation vertex. So in the following, we will define all these sets, all these sets. So this we will use the to define the new graph. So the first one is M0V. So this is the predecessor for the set. for which only contains V. So this is a subset of E0, and then we can define MNV inductive in this way. So this is the predecessor for this set. This is the union for this is the union for n minus 1 with another set. This set we defined here. This contains all the ranges of edges which starts from mn minus 1, but it does not start at V. So this is R. So this is Rn minus 1 V. And then we do the union for these two subsets, and we have the predecessor. Okay, so now this n actually is greater or equal to 1. Then we have for any n which is greater or equal to 0, we have MNV, which we defined above. So now we have the union for all these MNV. So we denoted by MV. And we also have another set NV. This is a set consisting of edges such that its range is belonging to MV. So this is NV is a set which contains of edges. MV is a subset of vertices. Okay, so now we will give the definition for the bifurcation splitting. So we have E is given and V is the bifurcation. So the V is the bifurcation vertex. Now the bifurcation splitting graph, we denoted by EV. It is given by this data. So we have the vertexes for this. They are the vertexes that has two parts. The first part are the vertexes from E0, but it's not in MV. The second part, let's see, this is a union for MEV. So MEV actually is defined here. So this is let's see, this is we take WE. So E is any edge starting from V. WX is a vertex in MV. So we can see from here, MEV, it's we can see it's a copy of MV, but we denote this vertex as W with an index E.
Sorry, Juan. So these are disjoint copies that you formally add and label one for each. I mean, okay.
Yes, disjoint. Disjoint ones of this. Yeah, you're right. Yeah, so it's we can see this MEV, those are all the vertexes with label with the label E. So let's see. So let's pay attention to this E. This is an edge from this is the edge starting from V. Okay, so this is the vertex set. For the edges part, it also has two parts. The first part are the edges, which is in E1, but it's not in NV. So NV is the one we defined before here. So NV. So, but we collect edges not in NV. This is the first part. The second part again is a union. So the union for NEV, each NEV is edges in NV with index E. So we write this is FE. So this is this is the index. Sorry. Oops. Sorry, I touched some. Oops. So here, so this union, we can see those are some copies of NV, but with labels. So we also need to give the source and range maps for this EV. Actually, we have several cases. We can give the definition case by case. Yeah, but I think maybe we skip this detail, and we can see an example. How can giving us a graph E? Yeah. How can we have EV? So basically, see, it's like this. So let's see. We have this graph E. So V is the middle vertex. So this is the bifurcation vertex we choose. We choose this V. So in order to write down the graph EV, we need to calculate the MNV. So for M0V, this is the predecessor for the set which only contains V. So that means we need to look at the graph. So the predecessor for U, that would be for V, sorry, the predecessor for V, that would be U and W. And of course, we should contain V itself, right? So M0V would be UVW. And then in order to calculate the M1V, we need to calculate the R0V first. And R0V, by the definition, it is, we need to look at the vertexes, which is not V, so that we need to look at U and W. We look at the edges starting from U and W, and we collect the ranges of them. So that would be UV again. So the R0V would be UV. Then M1V would be the predecessor for the union of this one and this one. So it's again, the union is UVW. And we see the predecessor for UVW is again UVW. So M1V actually is equal to M0V. Then we can see M2V is the same as M1V. And so MV would be M1V, because we have, once these two are equal, then all the MNV would be equal to M0V. So we have here MV, it contains three vertices, U, V, W. And MV, let's see, these are some edges whose ranges are in MV. So we look at all the edges here. Only IJK, we have the ranges are in MV. And for all the other edges, the ranges are not in MV. So NV would be this IJK. So now we will write the new graph EV as follows. So it's like this. Actually, for vertexes, so we have two parts. The first part are those not in MV. So it's X here. Oops, sorry, here. That's one Y here. So that would be X, Y, and Z. Those are the vertices which are not in MV. And then we have copies of MV. So this is actually, these three vertices are copies of MV with label E. And these are the three vertices. So which is a copy of MV, but the label is F. So this is, the label is G. So we have three copies of MV. So, and for X, yep, sorry.
Yeah, no, I'm sorry to interrupt you. So is the idea to eliminate the bifurcation? I mean, do you always get the graph where the V in question emits in the new graph? It began being a bifurcation point, so it emitted at least two edges, and now in the new graph, it emits a single one. Is that always the case?
Yes, I think, yeah, yes. So before this, in the original graph, it's a bifurcation, but now it's this V is separated, but it's not, but maybe it's not separated by separated into one by one. If we have some loops, yeah, I think we have some examples that those loops, it's always, it would be copied in each in each connected component. But for a certain part of edges, it would be separated into one by one. So but not all. We have some situation, if there are loops, those would be copied also. So it's like those. Yeah. But because, yeah, as you already, yeah, as we observed that this phenomenon happens, so we call this bifurcation-splitting. We call this new graph the bifurcation-splitting of the graph E at the vertex V. Yeah,
So,
but
if I start with if I take the graph that has a single vertex and what do I get?
Oh, sorry, you mean if V is a sink, do you mean this? Oh, you mean, yes, there's only one edge starting from V.
No, I mean loops. You take
loops.
loop.
Yeah. For loops, they will come back. So let's see. So let's give another example. Yeah. So this is this example. Sorry. For the edges, maybe we look at one glance. For the edges, so we collect those edges which are not in NV, E, F, G. So they are here. This is F, this is G, and all the other edges would be copied. So this, and this. Yeah. But I have, yeah, this will has the good question. So I have actually I prepare in the very end a graph which has cycles. So
okay, I'll wait till the end if you want.
Yeah. No worries. In fact, I should put it following that example. Yeah. I think. So let's see. Suppose we have this graph E. Oops. And this is our bifurcation vertex V. And so we can see here it has a loop. But it also has exits. So there are some edges going outside of the cycle. But it also has some edges. So it's not coming back to V anymore. So the new graph we can actually we should calculate M0V, R0V, and M2V, M1V. Actually, this is this. And MV contains U, WV, XR. So this part, yeah, this is our MV. And we can draw the new graph EV. EV would be like this. So let's see, we have a component here. So that means this cycle part, it's separated. It's here, and we have this component. And for these three edges, FGH. So we have FGH, but all these parts before this V, they are copied. So these are copied. So we have. So actually, we can see these are all these copied things, and then we can see the other graphs. For those parts, this picture actually, this part is kept as before. So that's so for this part, because this part it does not go back to V, so they are kept as before. So the separating, for this bifurcation V, we can see it's split, actually split one part. This is the loop, it's split that part, and this is split. We think it's split like in this way. So for me, I think I think we split all these kinds of edges, which start from V, but they could not go back to V. for these edges, we separate this into one by one in the new graph. So it's like this, FGH. Yeah, this is the two examples for the bifurcation graph EV. Let's go back to the page before. Yeah, so this is actually these two examples. So they show that how can we have this new graph EV, and then in the following, actually we would like to establish a connection between the Leavitt path address for LE and LEV. So this is our second part. So actually for Leavitt path address, it was introduced more than 10 years ago, almost 20 years ago, by Ra, Morno, Pardo, and Abrams around the panel independently. So here, actually, I think I just write the definition for Leavitt path address here. So yeah, actually for I think for us, so for Wheeler and Rusby, and also I saw Raman. I know you all know this Leavitt path address.
Yeah.
So
I know that.
Yeah. So I just maybe briefly say we have the notation. I use notation LKE. K is a field. So and we sometimes I simply write LE. And we have this is the quotient algebra. The first we have the free part generated by this E0, E1, and E1 star part. And then we have relations 1, 2, 3, 4. So for here, shall we go through these relations, or we can skip this?
We can skip that. Yeah.
Yeah. Good. So yeah. So actually here, so I just want to mention for this situation, I consider the regrading for Leavitt path address. So for regrading, so we have actually the grading for, we use the grading for we use the length of a path. So that means for paths with real edges, it has the positive length. For those star of a path, those have minus negative length. So we have the natural gradient for Leavitt path address. So my aim now in the following want to define a map between these two Leavitt path address. So I want to define a map gamma V from LE to LEV. So we just look at the generators. So for vertex, pick any vertex W. So the image we have two subcases. So because W is either in MV or not in MV. So we have these two cases. If this vertex is not in MV, then the image would be W, because this is also a vertex in EV. If W is in MV, then we use sum of WE. So E is an edge which starts from V. So this is the image for vertices. For the image of edges, for any edge, we have if its image is H, if H is not in MV. When H is in MV, we will use sum of these copies. We use the sum of HE. So for the star, so actually this is the star of this image of H. So we have this, and actually one can check directly that this gamma V is a K-algebra homomorphism, and we can see it also preserves the Z grading. So actually, we use Tomford's unique theorem. We can see that this is an injective algebra homomorphism.
So you mean so you are always over the field, right?
Sorry, always they are always.
Yeah. So this is the Kunz-Krieger uniqueness theorem. Translated
Yeah.
hypothesis. Okay.
Yes. This is we use it for as Z-graded algebra. So we when the image for this when the image gamma v for the vertex W is non-zero for any one, then we can deduce that this gamma v is injective. Yeah, this is the Tomford's unique theorem for Z-graded case. So in the following we have a natural question is when this gamma v is surjective. So we hopefully we can find sufficient and necessary condition for this gamma v to be an isomorphism. Yeah, as it's already injective, so we just need to look at when it's surjective. Yeah, if we find that condition, then we find a condition that gamma v is an isomorphism. So then we can find the condition for gamma v to be an isomorphism. Yeah. So in order to introduce this condition, we have some notation here. Oops, sorry. So we define path UW. This is a set contains our path starts from U and ending at W. So actually we found that we have, this is our first result, the main result that for E, any graph, V is the fixed vertex, which is bifurcation. And we have that gamma V here, gamma V, this gamma we just defined as above. So this gamma V is surjective if and only if we have this condition. The path from W to V is less than infinity, but is greater than 0. This is for any vertex in MV. So this is so we can see this is gamma V is an isomorphism as Z-graded algebras if and only if this condition holds. Yeah, so as we already have. So properties.
If you have a loop at V, you have if you have a not just a loop, but you call it closed path at V, then this condition is not satisfied because then you have infinitely many, right?
You mean if my graph has, sorry, I did not.
So if you have, so V belongs to MV, doesn't it?
Yes.
Okay,
yeah,
so
yes.
if there is a closed path at V, then you have infinitely many paths from V to V.
Yeah. So that. So
then that condition is not satisfied. Yeah. Okay.
Yeah. You're right. Yeah. So when V has a loop there, then this gamma V is not just isomorphism. It's not surjective. So actually we can see. So it's like we need for if there are any closed paths ending at V, then this gamma V is not surjective. Yeah, in fact we have that. Yeah. Okay. In fact, for the proof for this theorem, I think we just prove we use element-wise proof. It's like so we for this direction for the necessity. So we suppose we does not have this condition for some W. Then we see that we can construct WE has, we can claim that WE has no preimage. And for the other V, we will prove WE has preimage for any W in V and for any edge starting from V. So if we can show WE has preimage, then we can easily show that all the generators of LEV has preimage. Then we can prove that the sufficient condition also holds. So we can show that gamma V is a surjective map. So we just need to look at the generators for LEV. Yeah, okay, so it's like this. I will not give details for this anymore, but I mean that here we just prove use element-wise argument. Then for the last part, we will only consider the finite graph case. So that means E is a finite graph. So in this case, we have a question. So when gamma V is the gamma V we define about, when it is an isomorphism of Z-grid algebras, so definitely it implies LEV are isomorphism as Z-grid algebra. But we want to ask whether this is if and only if. That means we need to answer if gamma V is not an isomorphism, then LE and LEV are not isomorphism as Z-grid algebras. So this is our question. We want to figure out whether this holds. So actually the answer is yes. So this gamma V, this map actually is very special. Actually we can see that it induces, it can help us to deduce a map between the set of hereditary saturated subsets for E and EV. So we can have a positive answer for this. So in order to prove to have that, we look at hereditary saturated subsets. So we have a lemma for hereditary subsets. So we can have a map from the hereditary subsets of E0 to hereditary subsets of EV0. And we can prove this is an injective map. So the map actually is defined in this way. So we have a hereditary subset H over E0. We split it into two parts. The first part, H1, is contained in E0 set minus MV. The second part is contained in MV. The second part, H2, is contained in MV. And then the image for this H, we would put it as H1, because H1 is not in MV. So this H1, it contains vertexes in EV0. And this part, this is copies, some copies of vertexes in H2. So we pick any W in H2, we have WE. We collect all those WE. E is an edge starting from V. So actually we need to prove this is the injective map. Because the gamma V, the map, the algebra homomorphism gamma V is an injective map, but it could not guarantee this is injected directly, but we can prove that. So we have this lemma, and then in the following, actually we need to use homomorphism the correspondence between the graded ideas for Leavitt path address and the hereditary saturated subsets for E0. So let's recall that. So for the notation LGR, LE, this is the lattice of grid ideas of LE. For HE, this is the set of hereditary saturated subsets of E0. So Tom Ford actually gives this one-to-one correspondence, and he wrote down these maps already. So here we actually, for us, our aim is to define a map between HE and HEV. So we use this diagram here to define this map zeta. So we first, let's see, we can begin with H here in HE. So actually this H corresponds to some, it corresponds to some I, which is a graded idea in, which is a graded idea of LE. Then we can use gamma V, this map, gamma V here. We have a gamma VI. This gamma VI, this is image, the image of I and gamma V. And then we use this set to generate a graded idea for LEV. And then we again use homomorphic correspondence. Here we have in this direction, we have a hereditary saturated subset in EV0. So then we can define, this is how we can give the map zeta here. So actually, we write down the map zeta here. So we pick H, which is hereditary saturated. And the image would be this, the saturation for the hereditary subset rho H. As before, we prove that we have this lemma here, though H is hereditary. It's already hereditary. Yeah, we need to prove that it's hereditary. So for hereditary set, we do the saturation. We can have a hereditary saturated subset of EV0. So we recall here that this saturation of a hereditary subset is the smallest hereditary saturated subset, which contains rho H. So once we have this map between these two sets, actually these two lattices, we can have our second main result. So here we need E to be a finite graph, and V is a bifurcation vertex. Then we see that gamma V is an isomorphism if and only if this two-level algebra is isomorphism as Z-grid algebras. So actually we can we give a graph which is a sketch of the proof for this theorem 2. So actually we see for the proof for this direction, yeah, this is immediately right. Because if gamma V is an isomorphism of Z-grid algebra, definitely LE and LEV are isomorphism. So we only need to consider this direction. So that means we already have LE and LEV are isomorphism as Z-grid algebras. So we suppose gamma V is not surjective. We want to have a contradiction. So actually I draw this diagram here. So now we suppose gamma V is not surjective. So we begin from here. Then we use our first theorem as there we have an if and only if condition. When gamma V is surjective, we have if and only if condition. So when gamma V is not surjective, that means that condition does not hold. So this is, so I write this. This means this condition does not hold. So this is if and only if. And then we use this condition, we can prove that this zeta map, which we defined before, it is not surjective. This is we need to prove. So prove that. And then we use Tom's result. Because this zeta is not surjective, but before we recall that zeta is always injective. Yeah, this we proved before. But E is a finite graph. It has only finite many hereditary saturated subsets. So that means the lattice for grid ideas of LE and LEV, they are not there's no one-to-one correspondence between them. Then we can argue that these two algebras are not Z-gridded.
So your argument is that one set has less elements than the other, and that's why.
Yes. You're right. Yeah. Yes. So for this, we only need to prove this direction. So we only need to prove that. So this is we can only consider for finite graph case. Yeah, because we need to count the number of hereditary saturated subsets. Yeah. So this with when we have this theorem 2, so in this case, I think this gamma V, this is a very special map. So it can really distinguish LE from LEV. So actually in the, I have the last point here, is that actually this bifurcation splitting, it has a relation with after splittings. Yeah, actually after splittings, actually people, there are many, I think there are several papers, but here I think this paper by Bates and Pass, they in this journal, they published the paper in 2004. There they consider out splittings already. So here actually bifurcation splitting has some relation with outer splittings. It's like this: we need to give a certain condition. As here, I did not give details for this, but we have a certain condition. In that condition, the bifurcation splitting would be can be obtained by finite steps of outer splittings. So that means we have we have EV. So we use bifurcation, we can have EV, use bifurcation splitting. But this we can think this is we begin with E with several outer splittings. I use this. So they have some, so each step is outer splitting.
Okay, but so the conditions must imply that.
Yes. We have that condition.
That the Leavitt algebras are isomorphic because they.
Yes. Because outer splitting, it gives us isomorphism Leavitt algebras. Yeah, you're right. Yeah. So we need gamma V is isomorphism or surjective. Yeah, and then also need some condition. So it's like that. Yeah, so we have this, and this condition we can actually one can show that this bifurcation splitting is exactly several outer splittings. Yeah, I think this is all that I prepared for my talk. Yeah, so thanks.
Okay, thank you very much, Huanhuan, for a very nice talk. Are there any questions from the audience?
Just a question you were asking about one breaking in loops.
Yeah, well, so Ruth is telling me, is asking me to ask you about again. So if you can draw a picture of what the bifurcation split of a graph consisting of a single vertex and n loops, how does it look like?
So let me...
Loops, by loop, I mean an edge, a single edge that goes out of the vertex and lands again in the vertex. So a path of length 1 and several of them.
So a loop.
Yeah, and then another one, n of them. No. All loops.
The one that you get Ln out of it.
The one whose Leavitt path algebra is Ln. Yeah, that's L2 and that's L3. Yeah, so there.
Oh, I see. Ln.
Yeah. So, and then if you take the bifurcation splitting at the only vertex this has, what do you get?
Let's see. So let's see. I will calculate M0V is V. So because we only have one
Yeah.
V, then in this case, MV is V. We only have one vertex. And for our EV, by definition, zero for this is E0 set minus V, uniting all these copies.
So you have in this n copies of n V's.
Yeah. Yeah, n copies of this V.
Mhm.
Yeah, okay, let's see the EV1 edges. So E0 set minus NV. So NV here, all the vertices are all this E1, EN. So this is nothing. So we union all this NV. So E in S inverse V. Let me see.
And B sub E, right?
Okay, and then we draw this VE1, VE2, VEN. So I think this should be this, all these copies. This should be E1, E1. All this labeled with E1. E2 labeled with E1. And this would be all this labeled with E1, E2, 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 EN, E2. This would
Okay,
be E1.
So you get something disconnected.
Yeah, so this case is disconnected.
Yeah,
So-
so it's not Morita equivalent to the original one. Not just not isomorphic, not Morita equivalent either.
Yeah, yes. Yes.
So, and did you look at when I mean, when the map, the gamma is an isomorphism onto a full corner?
When gamma is
Onto a corner. So is that isomorphic to the corner of gamma V1?
when this is isomorphic to a kernel for LEV.
Yeah.
That. Oh, I have not considered that. Not yet. I don't know.
Okay. Yeah, so that's the next question. What if this happens to be true, then when P is full?
Then this is isomorphism as algebra. Yeah.
Yeah.
This is more.
And I mean, one other thing. If you have a Bratelli type of diagram, so like the diagram that you have when you look at the degree zero part of the Leavitt path algebra, and the diagram associated to the inclusions, right? The L01, L02, etc. Right. So I mean LE0, you write it as a filter union. L0 ends, and the maps between. So these are all metatial rings, and then the maps are given by you get a graph out of this, right? Okay, so this is an acyclic graph.
Yeah.
Which usually is infinite, but it usually does have bifurcations. So since there are no, since this graph is acyclic, then perhaps it is true that I mean you can by a process of bifurcation splitting, doing it many times, you can remove as many bifurcations as you want and get an isomorphic Leavitt path algebra. I don't know. I mean, what purpose? Because it's infinite, right? So Maybe when you you never remove all of them, but maybe I thought maybe your interest was to remove. I mean, you don't like applications, you want to remove them for some reason.
I see. So for cyclic finite graphs, for example, for this, we when we split there, we have this graph. So this is the new graph. So this is that. So you mean we can? Yeah.
That is isomorphically pathological according to what you.
Yeah. Mm.
Yeah, but if the graph is infinite, you're never done removing bifurcations. Right?
You mean this is just a cyclic, not finite graph, right? Sorry,
Yeah,
I did
because
not.
I mean the same graph repeated infinitely. I mean, so it's
For example, I think is that let's see.
so the graph. You know this cover, the universal cover of the graph. This E tilde.
Universal corner.
Yeah, the fiber is the integers. So this is this graph, the graph I'm referring to. So you say you have say the graph with one vertex and two loops, right? And then you split this, and this becomes then this becomes a sequence, an infinite sequence of vertices, such that from vertex n to vertex n plus 1, you have two edges. Right? So like the colimit that defines n to infinity, which is precisely the 0-degree part of the Leavitt path algebra or of this graph.
Sorry, I think I lost somewhere. So sorry, Vela.
Yeah.
So we begin with this E. Is that we begin with this E? Where?
Yeah. So you start with this E, right? So
yeah.
Okay. And now instead of one vertex, so the universal cover of this graph contains a countable number of vertices. So say vertex 1, 2, 3, 4, etc. And from vertex n to vertex n plus 1, there are exactly two edges. So from B1 to B2, there are, that, everywhere.
Okay.
So you have bifurcations everywhere, right?
Yes.
So, and then you could remove, you could split the bifurcation at every, I mean, by an infinite process, I suppose. And then I think because this has no closed path, there are no closed paths, it's a cyclic graph that you get, you should get an isomorphic Leavitt path algebra. So the Leavitt path algebra of this new graph is M to infinity.
M to infinity.
Yeah.
Is that?
Yeah, no, 2 to the infinity. Infinity is a power of 2.
I see.
So that's the 0-degree part. That's the 0-degree part of L of the Leavitt path algebra of that E that you wrote.
I see. I see. Okay. I see. This. You mean you want to see this? Right?
Yeah. And then so I thought that maybe to a graph like this, you can apply your construction infinitely many times and then get a graph whose Leavitt path algebra is isomorphic to this one and which has no bifurcations. I don't know what the purpose that would serve, but
maybe this is so simple, it would be the same as out splitting. Because
Maybe it's yeah. So
Mhm.
Bruce, who for some reason wants to talk through me instead of unmuting himself. Yeah, so yeah, he said that in this case you maybe get the same thing as the out splitting.
Okay. Okay.
But anyway,
Yeah. Anyway, I think this is good. Yeah. Thanks. Yeah. Thanks, Ollie.
what was your motivation for studying this bifurcation splitting? What did you have in mind?
Actually, yeah. Actually, before we just try some easy examples like this, and then we see. Oh, okay. We can find a general contraction. Yeah, it's like that. Yeah, but yeah, it's yeah, but yeah, I'm not sure whether I can connect this with some like some other directions, but I have not yet. Yeah.
And
Yeah. We're beginning, so it's like we just want to like do a little modification on the graphs, and we want to see whether we can know the algebra structure for the Leavitt path algebra. Yeah.
And do you know, I mean, from the point of view of the incidence matrix of the graph, so do you stay in the same shift equivalence class or some equivalence class?
Some equivalence, sorry, some equivalence class for, sorry,
For the
I did not.
So if you take, so you know that the matrices of, so you have two graphs, finite graphs, say E and F,
Yeah.
and then
Yeah.
without sinks, say.
Yeah.
And then or even if you want without sources too.
Yeah.
And then you consider the incidence matrices of E and F.
Yeah.
Okay. Then you know that the A, E, and AF are shift equivalent. So yeah. So shift, no, not shift equivalent. No. So that strong shift equivalent if and only if you can pass from E to F by a series of out splittings, in splittings, amalgamations, blah blah blah, right?
Yeah. Okay.
Yeah, and so several moves which are out splittings and in splittings and their inverses, right? So now you add a move. This bifurcation splitting.
Yeah.
So if you declare two matrices to be equivalent, Huanhuan equivalent, if you can pass from one to the other by any of these moves, and additionally you allow a bifurcation splitting, then you get a new notion of equivalence for the matrices. And well, I mean, one could ask where in the hierarchy of equivalence relations between matrices does this sit? Because of the all these problems and conjectures relating the various notions of equivalence between the matrices and associated shift spaces.
Yeah. Equivalence between, yeah. See. Yeah, this is, I think this is this should be a direction considered. Yeah. Yeah. Okay. Yeah. Thanks. I think this is a good question.
Okay, so are there any further questions from the audience? If not, I'm
Mm.
going to stop the recording. Right?
Yep. Okay. Yep.